Today we're going to take a look at section 4.5, which is called the fundamental theorem of calculus. Anytime in mathematics that somebody puts the fundamental in front of it, it probably means it's important and you should pay attention. Sound good? So that's exactly what this is. This is really important. It is very crucial to calculus. And so that's where we're going to actually be finding our time spent today. And we are going to make a lot of connections between the sections that you've been doing that seem a little bit disconnected and how they all interrelate. So here, to start with, is the fundamental theorem of calculus. There's two parts to this theorem. So this is part one. It says if f is continuous on an interval, capital F is the antiderivative of lowercase f. Then the definite integral, that's a notation we learned last time, between a and b of f of x dx is the antiderivative, capital F, evaluated at the point b, minus the antiderivative, capital F, evaluated at the point a. Okay, so after you get that written down, somebody tell me, how did we calculate this last time? What have we done to try to find what a definite integral, that is the area under the curve, would be? What methods have we tried? We did what? Graphing. We did it with graphing. What did we do after we graphed it, Cooper? Do you remember? Shading. Okay, we shaded, but how do we actually find the area of the shading? Okay, into what? Because plugging in the numbers just finds the location on the curve. What did we do once we plugged in those numbers? What did we do? What was the purpose behind plugging in numbers? Not sure? Okay, that's all right. Snyder.
We broke the graph into like 4 different sides or lines.
And what shape did we make?
Rectangles.
Rectangles. Okay, so one of the ways we did it with an approximation was we did it with rectangles. So we got that shading, and it wasn't exact, and we knew it, but we shaded, and we said, okay, well, we can estimate the height of these rectangles using either the left endpoint or the right endpoint or the midpoint. Are you guys with me? But it only gave us an approximation. We talked about the fact that if we had more rectangles, the approximation would be better, right? But there comes a point when we don't want any more rectangles, either for the sake of time or efficiency or something like that. Okay, so one way we did it is we did it with breaking this interval into smaller pieces and making rectangles, either under or over or nearby the curve. There was one other way that we did it. Geometric shapes. So some of the shapes that we had actually were geometric. So we did one in class that was a trapezoid, right? The actual shape was the line. It was a line that we were finding the area underneath, and we recognized that shape actually is a geometric shape, a trapezoid, so we have a geometric formula that we can use. And that's great when we have a geometric formula we can use, but of course if we were dealing with, like, say, a parabola, it doesn't have that feature, so we can't do that. Okay, so this actually tells us how we can find, it solves two problems at once. It solves the problem of finding it exactly versus an approximate, okay? And it also solves the problem of not having a geometric shape underneath it to actually find an exact value of with a geometric interpretation. All right, so what does this say we're going to do? Well, it says we're going to take an antiderivative, right? That's what this notation is right here. We need an antiderivative, and you know how to do that, all right? You guys are still in the middle of doing a skills quiz for me, most of you, right? Most of you are still in the middle of doing a skills quiz. A couple of you are done. That reminds me, actually, remind me when I'm done with this, when I need to talk to you about my office hours today. But we're doing these skills quiz. So that's antiderivatives. Agree? Okay, great. And then what we can do with that antiderivative, this says, is that we can actually evaluate it at the endpoints that were given on our interval. So we evaluate it at the upper endpoint, we evaluate at the lower endpoint, and we subtract their difference. We subtract their sums, their values. All right, so this is the first one. So let's actually do an example. This is one where we could do a geometric interpretation because negative 3x plus 4 is a line. There's nothing really exciting about it. It is a line, so we could do a geometric interpretation. We're going to do this with the fundamental theorem of calculus, though. So according to the fundamental theorem of calculus, basically what we're going to do is we're going to start out by finding this antiderivative. Okay? So what is the antiderivative of negative 3x? Does everybody agree with that? Look good? Awesome. What is the antiderivative of 4? 4x. Good. All right, so notationally what we do next is we draw a vertical bar at the end, and we put our limits of, or our interval endpoints at the top and the bottom of that vertical bar. So 5 goes to the top, just like it was the top before, 2 goes to the bottom.
Do we not put C?
We don't need to put a plus C. In fact, you know what? Let me put plus C in there, and I'll show you why. And then we won't do it after this. That's a very good question. Sorry, I did not think about mentioning that. So let me actually show you why that happens, and we don't need it. All right, so 5 goes to the top, 2 goes to the bottom. Everybody good so far? Okay. Now the next thing that the fundamental theorem says is that we can take those values and we can evaluate them into our antiderivative. So we're going to do one all out longhand, and then I'm going to show you a shortcut on your calculator as well. So we're going to actually plug in the number 5 everywhere. So this is evaluating at 5. And then we're going to evaluate this at 2. I'm sorry, I have an X still left over here. How did I do that? Let me get my 5 left in there like I was supposed to. Then plus C at the end here. Does that look okay? Let's deal with the plus C first. What's going to happen to my plus C? It's going to cancel. There's a C here, and there's a C here, and there's a subtraction sign in between. So those add to 0. And that happens every single time. So since that happens every single time, we don't actually need to put the plus C on when we're doing definite integrals. That is, the integrals with the numbers at the top and the bottom. All right, so we don't need the plus C part. The rest of it we could evaluate with our calculator. We could evaluate this one pretty cleanly, just maybe in your head. But what do you get when you plug in the number 5 right here? What is this piece? What was it, Allison? 57.5. What do you get when you plug in the 2 into it?
Isn't it negative 3/2 squared?
Yes, I left a negative off. Thank you very much. Thank you. Yeah, we do have a negative there. Perfect. What did you get, Kel? Negative what? 14. Do you have a second on that? The negative 14? Not quite?
It's 2.
2? I don't have this written down in pieces, so let me see. You got... Okay. Maybe a sign off on that one. Maybe the negative sign was missing, Allison. Negative 17.5. What do we got on the second one? Negative 14. Like this?
37.5 plus 20. Yeah, I got negative 17.5. It's, yeah.
Oh.
Sorry, I told you.
Okay, negative 17.5, and the second one was negative 14? Is it minus negative 14?
Yes.
Like this? Are we sure? I feel like I need to get a calculator because I'm getting different results. You think it's 2? Think it's negative 2? Okay. All right, it's okay. I'm going to show you how to deal with it without having to think about this much anyway. Is it minus negative 2? Okay. Okay, is this better? Oh, all right. Sorry. Are you guys over here telling me? Volume, project so I can hear you. Thank you. All right, the end result. Okay, this is good because at least this is the answer I have in total. I didn't have those pieces written down. 19.5 then, right? Negative? Is that good? Whew. Oh my goodness, that was way harder than I thought it was going to be. Okay, you want to try something a little bit easier so you can do it? I'm going to show you 2 different ways that you can do the problem. Are you ready? Okay, with your calculator. So everybody have your calculator out at the ready because it's going to be really handy. Okay, so the first way is that we're just going to let the calculator do the evaluation. So you guys have seen this one before, but just let me reiterate that this works, okay? So if you grab your calculator, I'd like for you to put in what we got for the antiderivative, except not the plus C part, because we've already talked about the fact that that's unimportant in the calculation since it cancels out. So just put that into y equals, okay? So you're going to put in negative 3/2 x squared plus 4x. Everybody good? I'm going to show you 2 things you can do in this genre, like with this piece of information. One thing is you could just go to the table, right? And you could plug in 5, you could plug in 2. And the table will spit out the negative 17.5, and it'll spit out the 2. Everybody good with that? Okay, so we've seen that. You've seen that before. We've kind of done that before, I'm sure. All right, another thing you could do, go out into the regular screen. Okay, regular screen. You've got this in Y1. Does everybody have this in Y1? Are we good with that? Okay, in the regular screen, I want you to hit vars. There's a button that says VARS, vars. I want you to arrow over to the right to the one that says Y vars, Y variables. Hit enter, because this is a function, and then hit enter for Y1. Does everyone now have Y1 on their screen? Like it just says Y1. Okay. You can't hit enter with Y1, but what we can do is we can use the Y1 as function notation. So next to Y1, I want you to put 5. Don't hit enter yet. Hold tight, because it can do cooler things than that. I want you to hit a minus sign. And I want you to go through the same thing again. Vars, Y vars, function Y1. Pull up Y1. And then put in 2. And your calculator will, in essence, be doing this exact... Let me cut out this because it's all cluttered up now. It will be doing this exact thing where it actually has the Y1 in place of where I've got F. And it has the limits on the top and the bottom, the endpoints, the interval endpoints, 5 and 2, in for the A and the B. Right? That's exactly what that notation should look like. Y1 of 5 minus Y1 of 2. You hit enter, it should give you negative 19.5. Does that work? Okay. Now, all of that is hinged on the fact that hopefully you found the antiderivative correctly, right? You guys with me? Now, if you made an error in finding the antiderivative, obviously you're going to have an error in the answer at this point too, correct? So wouldn't it be nice, when you don't have a back of the book on a thing such as an exam, to be able to confirm and to know in your spirit and heart that you did the antiderivative right? Wouldn't that be nice? It would be nice. It would be handy to make sure that you didn't make a mistake. So I'm going to show you another way to do that. Okay, so let me grab my calculator because I can't remember the first button hit push. Just a second. Okay, I want you to hit y equals and go ahead and clear out what you have in there and put in the original equation. So it should now say negative 3x plus 4. Okay? So does your y1 say negative 3x plus 4? Excellent. Now I want you to exit the screen back to the regular screen. Plain old blank screen, clear it out if you want. I want you to hit the button that says math. It's on the left-hand side. I want you to arrow down until you have number 9. Do you see it says FNINT with a parenthesis? Now, some of you don't have that notation. If yours does not say FNINT, let me know. Okay, maybe the next screen where it shows up differently. I'll make mention of it. All right, hit number 9 or select enter on top of the number 9. And some of your screens now actually say the same thing you just selected, like this. Whose says that? Raise your hand really high. Okay, about 2/3 of you. Do yours say something different? Okay, let me get you to where we are.
Well, we wrote.
Okay, that's good. Exit that screen. Hit math. And select number 9. Yep, there you go. Okay, exit the screen. Math.
Number 9.
Who else? Does anyone else not have FNINT? Yours looks different. Okay, that one, that's okay. I'm going to show you how to do it from yours too. What is yours? Does yours look like?
Got the integral script out.
Okay, good. We're going to do yours too. All right, somebody have here?
Yeah.
Okay, select enter. All right, yours is like that too. Okay, so those of you who have the thing that says FNINT, I'm talking to you right now, okay? It's about half of us at this point. So if yours actually says FNINT on the screen right now, pay very careful attention. I'm going to show you the notation you need to use next. All right, the notation that you're going to use, and I'll remind you how to get it, is you're going to tell it you want the function y1, you want the variable to be x, you want the lower limit to be 2, and you want the upper limit to be 5. Okay? So there's commas in between there. There's a comma on your screen. So you go to vars, y vars, function y1. Okay? You put a comma. You put an x. You put a comma. You put a 2. You put a comma. You put a 5. You close your parenthesis and you hit enter. Okay. Did it work? You got a negative 19.5. Okay. Does everyone who has the F and INT end up with the answer negative 19.5? Excellent. Okay, now, let me see yours for just a second, Alexa. All right, the other notation actually looks like the notation for our problem, like this. Whoops. Right? Okay, you're going to enter it in just like that. You can enter the negative 3x plus 4 there if you want, or you could enter y1 there if you want. So you could have 2 to 5 like this, y1, and then dx. That's the simplest way to enter it. Okay? So you have to have the x at the end. That's the piece that you enter. You have to have a 2 on the bottom, a 5 on the top, and you put y1 in the middle, or you could actually enter negative 3x plus 4. Looking good, yeah. Okay. And then when you hit enter, it should also tell you negative 19.5. Does it?
Yeah.
Did anybody's not tell them the right value? Okay, cool. So if you got the same thing both ways you did it, then that means you did the antiderivative correctly, right? Because the only way it's going to happen, unless some fluke accident, weird kind of crazy nuts thing that's like probability of 0.000001 or something, I don't know. You did it right. Okay, if you got the same answer both ways, you did it right. All right? All right, let's try another problem. I want us to, okay, so you might be asking, like, well, what do I have to show that if my calculator can do all this for me? You have to show me the antiderivative. That's the bare minimum you have to show me. So what is the antiderivative of 1? X. What is the antiderivative of sine of x? It is negative cosine of x. You have to draw the vertical bar here at the end and write pi and 0. That has to be on your paper. No questions. All right? The next thing that has to be on the paper is me understanding that you know that you're plugging in pi and you're plugging in 0. So notationally, if you want to write it like that, you can. If you want to actually show me the pi plugged in, the 0 plugged in, you can. That's fine. Okay? So either this or you can write out pi minus cosine of pi plus, I'm sorry, not plus, minus 0 minus the cosine of 0. One of those two things has to be written next. I don't care which one. Now, here's the trick on this one. Because we are using pi and we're using things with cosine functions, if we put this in our calculator, it's going to approximate that pi, right? And that's not going to be especially friendly. It'll give us an approximation. We can confirm that we did it right. But on this particular one, having the pi plugged in right here and seeing that part of it so that we can evaluate it, it's going to make a lot more sense. So I'm going to use this notation here at the end as my sort of stepping off point for the next piece. Do you remember what the cosine of pi is? It's what? Negative 1. So we have minus a negative 1 right here. And then we have minus. What is a cosine? What is the cosine of 0? Yeah, so we have minus from here, we have a minus from here, and then we have this one right here like this. So I got a lot of a mess going on, but because I got a lot of negatives. But this is really just pi plus 1, or pi plus 2. Your calculator will confirm it by doing an approximation for those values, right? All right, if we put in pi plus 2, it should be about 5.14. Agreed? If pi is 3.14. So we probably would recognize that pretty quickly. And you can confirm that with your calculator. So go ahead and take just a second. Use one of those methods that we just did. Either put in the original function and use that function integration math 9 button, or put in the antiderivative into y1 and just evaluate it at the pi and at the 0. And I just want you to confirm that your answer is approximately 5.14, which would be pi plus 2. So that's what you're looking for. You're looking for whether or not your calculator gives you an approximate value of 5.14. Okay, did it work? Did? Awesome. Okay, here's another part to the fundamental theorem of calculus. This is the fundamental theorem of calculus part 2. All right, so it says if f is continuous on the interval ab, and capital F of x is the antiderivative from a to x of f of t dt, then f prime of x, capital F prime of x, equals lowercase f of x. So, practically speaking, over here what this is saying is that if I take the derivative on both sides, the derivative, f prime, capital F prime of x, is just f of x. Now, notice in terms of notation what's happening. This a sort of looks like it gets excluded, right? It doesn't end up mattering. The reason that that happens is because what would actually happen over here, in fact, let me just show you real quick what would happen over here. Let me cut this and try again. If we were to evaluate this on the left-hand side or the right-hand side, we would take an antiderivative and we would evaluate it at the point x. And we would take an antiderivative and we would evaluate it at the point a, right? That's what would happen from the fundamental theorem of calculus part 1. What happens if I take the derivative of both of these? Well, the derivative of this is just little f of x. That's where it came from to begin with. What's the derivative of f of a? 0. It's just a number, right? I plug in something into my function, a number into my function, I get a number. Take a derivative of a number and it's 0. So that's why it looks like it sort of goes away. It does. It's constant. So we actually end up with the derivative. This is just saying that the derivative of the antiderivative, the derivative of the antiderivative is the original function. Sounded like a tongue twister, sorry. So the derivative right here of the antiderivative function capital F of x is the function little f of x. Okay? And in practice, let me show you what that means. And I think we're going to do this out of order. No, I'll do them in the order I've got them. That's okay. All right, so here we have a function f of x, and it tells us that the integral goes from 0 to sine of x of t plus 2 dt. How notationally is this different than this? What looks different about it? There's one really big difference. It's got a sine of x in the top interval endpoint, right? This one right here has an x, and this one has a sine of x. Do you guys see that? Okay. That is going to change a little bit of what's going on. And let me show you why, and then we'll actually talk about, practically speaking, what it means you need to remember to do. So let's actually attempt to calculate this directly for what it is, and then we will take the derivative of it afterwards, okay? So right now we're just going to figure out what this is. So what's the antiderivative of t? Good, t squared over 2. What's the antiderivative of the 2? 2t, excellent. And then this is going to be evaluated at sine of x at the top and 0 on bottom. All right, so we're going to put in sine of x. So this is sine squared of x over 2 plus 2 sine of x. And then I'm going to subtract 0 squared over 2 plus 2 times 0. So it's actually subtracting everything out at the end, right? It's all zeros at the end. So we end up with sine squared of x over 2 plus 2 sine of x. And this is our original function f of x over here. That is not what this question asked us to do. It asked us to find f prime of x. So now I need to take the derivative of this function. What is going to happen when I take the derivative of sine squared? How do I do that? Okay, the 2 will move to the front. Then what? It will, but not yet. What rule are we employing? There's a couple of them, actually. There's a chain rule here, right? So the 2 comes to the front, I rewrite sine, and then I have to take, to the power 1, and then I have to take the derivative of sine, which is cosine of x. I'm still over 2, and plus, and then I have 2 here as well, and the derivative of sine is cosine of x. And things clean up. I mean, like these 2's clean up. I end up with sine x cosine of x plus 2 cosine of x when I'm done.
It's not like when it's sine squared over 2, the over 2 is not changing.
Right, it's a constant multiplier. It's like having a 1/2 in front. So anytime we take derivatives or antiderivatives, if it's multiplied by a number, that multiplication factor never changes.
Okay.
Yep. Okay, so what's going on? I mean, like, we went through a lot of work. We took an antiderivative, and then we took a derivative all the way to get back to almost where we started, but it really doesn't even look like where we started, right? It looks like t plus 2, and now my answer looks like sine x cosine x plus 2 cosine x. That doesn't really look like what this is saying over here. This here almost makes it look like I'm not really going to have to do much work. And we just did a lot of work in that problem, actually, didn't we? Are you guys with me? So let me show you what this is actually saying we can do with this problem in the not a lot of work sense, okay? So let me move this to the side. All right, so what we're going to do instead, that is the easier way to do the problem, is that we're going to take a look at this, and we're going to plug in exactly what it said we should do. This actually says I should be able to take the x and just plug it into t and be done. That's what it says I should be able to do, right? Well, let's try that over here. If I take the sine of x and I just plug it into t, what happens? Well, over here, this is not equals, sorry. I'm finding f prime. And I'm doing that without doing an antiderivative and then a derivative by plugging in the sine of x in for t, and I'd have sine of x plus 2. What is different about that right there than the answer I got doing it the long way? The cosine. Why do I need a cosine here to make this actually correct? Where'd that cosine come from? When I did the derivative, what was the rule that I was using? What rule was I using that ended up giving me a cosine? The chain rule. Are you guys with me? It was the chain rule that made that happen. So what I actually have here is what exactly I just wrote down, but then it needs to be multiplied times the derivative of sine, which is cosine. So I have exactly the same thing as before. The sine of x times the cosine of x plus 2 times the cosine of x. The difference is that this right here is the derivative of the upper endpoint. That's part of it. You see, the other process, when it was written here to begin with, what's the derivative of that upper endpoint? 1. Right? That's why it looks so clean and simple, is that there really is it's there. If you want to think about it right here, we're saying right here this is multiplied by the derivative of x. It's just the derivative of x is 1. So you don't see it. It's kind of hidden. All right? So if our upper endpoint is anything besides just plain x, we multiply by the derivative of that when we're calculating this value. Let me show you a little bit different one. It has another feature that this one didn't have. What about this one looks maybe awkward or whatever? What looks different than the last one? What's that?
3 minus x.
Okay, I've got a 3 minus x on top. That's different than sine x. There's something else too.
We have x on top.
There is an x on top and there's an x on bottom, isn't there? It's there twice. So what we're going to do is we're going to actually use the, I can't remember where it was we saw it. I think it was in 4.2. There was a theorem that we had that told us how we could deal with the fact that an interval can be broken into pieces. Let me just remind you of that theorem real quick. It was saying that if I'm going from A to B and I wanted to stop midway somewhere at C, I could do that. And I could just go from A to C and then I could go from C to B, and that would be totally cool. Do you guys remember that? We're going to use that for this particular problem. So bear with me while I do a revision of this. What we're going to do is we're going to go from x to, and it doesn't matter what number you choose. So just pick your favorite. 0 is my favorite number because we use it a lot in math, makes things simple. It's not going to make any difference what we pick right now here. But I'm just going to write down that we're going to go from x to 0 of t squared plus 4 dt. And then we're going to go from 0, that's the new starting point, like the c in between, to 3 minus x of t squared plus 4 dt. Okay, is that step okay so far? All we did is we split it into 2 different pieces. Basically, up here in my diagram, what we're saying is that we started with x, this is 0, and then this is x minus 3. And it really doesn't even matter, I'm sorry, 3 minus x, that's what my numbers were. It really doesn't even matter which number is bigger or smaller. You can break it apart halfway between. It'll all work out in the end. You don't need to worry about that. Okay, now this second piece now looks an awful lot like my last problem. It doesn't have sine x at the top. It has something else, but it looks a lot like the setup of the last problem. I've got something with t inside. I've got a function at the top that I'm going to have to do a chain rule kind of thing with, but it looks a lot like that one. What about the first one? It looks awkward still, however. The x is on the bottom instead of the top, right? Well, that's not okay. It doesn't follow the pattern exactly like it should. So what do we have to do? Well, there is another property of integrals that says that we can switch the limits of integration. Now think what would happen in terms of this formula back here if I switch the limits of integration. Hang on, I'm going to write it down and then let you talk, Akil, because you got the idea there. What would happen if instead of doing f of b minus f of a, I did switch them? And if I switched the locations of these, what would happen in my calculation? I'm apparently moving my pen too fast for the iPad to keep up today. I would get f of a minus f of b, right? What would happen? What's the net change in what happens, Akil?
That's equal negative.
Right. This is the same thing we had before, but the opposite sign. You guys with me? If I subtract in the wrong order, I get the same number, I just get the wrong sign. I use this all the time in my calculator. When I'm calculating your grades, I just subtract whatever order I want, and I know it's going to be the positive part of my answer. Doesn't matter. So, what does that mean for us right now in this problem? Well, what it means is that I can change this limit of integration to go from 0 to x so that it matches what it's supposed to match. But what am I going to have to do to compensate? I'm going to have to put a negative in front of it. Very good. Does that make sense to everyone? All right, now the nicer piece of this actually is the first piece because it looks exactly like part 2 of the fundamental theorem. So we're going to evaluate this. So the first piece is going to be a negative. And then according to the fundamental theorem, what I should be able to do is to take this x and plug it in everywhere that I have a t. Okay? So I'm going to get x squared plus 4. If you want to think about reminding yourself then what's the derivative of x, it would be 1. If it helps you to see that every time so you don't forget it when you do need it, write it. You don't have to write it, but you could. And then we have addition for the next piece. same thing, fundamental theorem of calculus, part 2 says I can take the 3 minus x, and I can put it inside of where t is. So I can write this as 3 minus x squared plus 4, and that's perfect. But then I need the derivative of 3 minus x, which would be negative 1. Much simpler derivative than the last one, actually, since it's just a sign change. And then all we need to do is to clean this up and simplify what's left over. Okay, so that's what we're going to do. I want you to just take about 1 minute, clean that up, and compare it to somebody next to you. Let's make sure everybody has all the same things. This is just an algebra exercise at this point. When you get done and your neighbor gets done, look at your neighbor and say, did you get this? Make sure that you have the same thing. Got some negative signs, you got some distribution. It's easy to make a mistake in the algebra. You guys all know that. I make mistakes in algebra sometimes too. I shouldn't admit that, should I? Whew. It's scary to hear that from a teacher, I know. Okay, what I have is negative 2x squared plus 6x minus 17. Is that what you guys got? Is that what we have over here? Huh? It's on the board. Yeah, I wrote it down. Negative 2x squared plus 6x minus 17. Does that look okay? Let's see. I would have a 9 from in here. I will have a negative 4 from here. And then I'll have another 4 from here. Oh, it's a negative 4 because there's a negative out here in front. There it is. So I have 9, 4, and 4. So that's 17. They're all negatives, actually. Are we good? Excellent. Okay, let's see what this actually looks like in practice in a problem now, okay? Like with not just find the antiderivative kind of stuff. So we're going to go back to another problem that looks like it's got some language involved. We're going to have to make some determinations based on the language. It wants us to find a given area, and it says it's the area of the region bounded by the curves y equal x squared, x equal 2, and the x-axis. And this question is just begging you to do what? Graph it, draw something in order to figure out what it is you're actually doing calculus on. Make sense? Okay, so we're going to draw an axis. That's not very good. Let me try that again. Better. All right, we've got the graph of y equal x squared. What does that look like? Parabola. Fabulous. So we're going to have something that looks something akin to that. My graph's not meant to be perfect. It's meant to give us a visual, okay? What does the equation x equals 2 look like? Which one is it, Jacob? It's this. It's a vertical line, right? Vertical line at x equal 2. So I'll draw it in blue. So here's my vertical line at x equal 2. This was my line at y equal, or my curve at y equal x squared. And then I've got the x-axis, which is the horizontal axis on the bottom, right? So that's this line right here. It's my x-axis. Can you see the region that it's referring to in the description? You see the trapped region? It's talking about this piece right here. I didn't draw it well. I need to learn how to color in the lines better, but that's the basic region we're talking about here, right? Okay, so we know from what we've talked about already that this means I'm finding a definite integral. We have to make determinations about the rest of it ourselves. Let's go from left to right. So the leftmost thing we need to do is we need to figure out what numbers go here and here. Any idea what those might be with this picture? 0 to 2, exactly. So the lower value is on the bottom, so the leftmost endpoint, and the upper value is the rightmost endpoint on top, 2. We need to put an equation in here. The equation, not equation, excuse me, an expression in here. The expression that goes inside here comes from the equation that we're bounded by. That is, what equation says I want to be below this? It's y equal x squared, right? This orange one right here. So the expression that goes inside here is x squared, because that's the curve that I'm bounded below. I need to be below that curve. And then you need to put the dx on the end. And I know that right now the dx doesn't feel very important. And I know that not all of you will get to the point where you'll realize and figure out why it is. But it does happen later in calculus. That's very important. So, oh my goodness, I almost fell. Sorry, my back's bothering me today for some reason. Okay, so we do need that dx at the end. What that dx tells us is it tells us with respect to x. X is my variable. That's all it's saying, is the variable in the problem's x. I know you know that in the problem, but there will come a time when that actually matters and it really makes a difference. So, now we're ready to do calculus. We've set everything up. We need to find what? We need the antiderivative, the integral value. Okay, so what is the antiderivative of x squared? Right, 1/3 x cubed, or you could say x cubed over 3. And we're going to draw that vertical bar for evaluation from 2 down to 0. We could use a calculator, but honestly, this is a pretty straightforward evaluation, so I'm not going to bother with it. I have 1/3. I have 2 cubed. And then I technically have the 1/3 and 0 cubed. Obviously not a very exciting value. What is the grand total that we have here? 8/3. Now, would you like to see I think this might be the last cool thing that I have to show you on the calculator maybe this semester, actually. You want to see it? Okay, I want to show you something really cool. Okay, take your calculator. I want you to plug in the original function into y1, so x squared, okay? So y equal x squared. So y1, it's got x squared plugged in. The next thing I want you to do is I want you to make your window the standard graphing window. So the way you do that is you hit zoom, number 6, and it puts it in the plain old standard 10 by 10 window. Is everybody good with that? All right, so I think actually it might help us to make the window a little bit tighter. So let me correct what I'm going to do. I want you to hit window. You'll think it's more fun, I think, if we make our window a little bit tighter. Let's just go from -5 to 5 on y and -5 to 5 on x. So change x min to -5, x max to 5, y min to -5, y max to 5, and then just hit graph. And all it does is it zooms this in a little bit closer. You could also use the zoom in feature. That would have been fine too. Okay, does everybody have this basic picture right now that we have without the shading and the extra lines and stuff drawn in? Okay, great. I want you to hit second, trace. And you should have a menu at the top that says calculate. Is everybody inside of the menu that says calculate? Are you there? Awesome. Do you see number 7 on that list that looks like this definite integral or this integral notation that we've been using? Select number 7. On your screen, it says lower limit. Does everybody say, or maybe left endpoint or something like that? What's the lower limit or the left endpoint that we're calculating this problem? 0. So you can actually hit the number 0 and hit enter. Okay? Then it says upper limit. What's the upper limit we're doing? 2. So hit the number 2 and press enter. Did everybody see something happen on your screen? Okay. Did it shade? Did your screen shade? Not yet? Okay, let me come take a look.
Okay. You have to know here.
Good.
Then the window.
That's good. I can do the graphs.
Oh, like
Great. Now you're going to hit second. Trace. That looks fine. You've got your little turned on. So maybe this is cool for us to just have this. Oh my goodness. What have you done, Ian?
Well,
-5, 1. Oh, you've got these backwards. -5, 5. Yay! All right, now I do second. Count. Number 7. Lower limit 0. Enter. 2. 0. Enter. 2. Enter. Okay. Did anybody else not get the shading? Did everybody see the shading? Here's something even cooler. I mean, the shading is super cool. Don't get me wrong. But do you see that at the very bottom of your screen right now it tells you a value? Any idea what that value might be? That's the area it just shaded, which should match what you just got on the screen, if that's right. Is that 8/3? Yes, it is. So this is yet another way your calculator can calculate this area, and it's very visual, which is super cool. All right, so this is a fun one. All right. I think we have one more problem to look at. Oh, yes. Okay, average value. This has a really good visual with it, too, but not with the calculator. Well, actually, I might show it to you with the calculator. I might. In fact, I probably will. Okay, let's take a look. Average value. Average value for integrals says that if you have a function f of x, and it's integrable, that means you can take the integral of it on the interval a to b, then the average value of the function itself on that interval is the area part multiplied by 1 over b minus a. Okay, so let me show you visually what this does, and then we'll do it when we do our example, we'll actually see it happen. So let's say that this is your curve. All right, starts at A, ends at B, and you find the area between them. And this is all fabulous. And it wants to know what's the average area. Well, what it actually does is it tells you a height that if you took the height, that wasn't a very good representation, maybe like that. It tells you the appropriate height that you could use with the width that's b minus a to create an actual rectangle that's the same area as the shaded area under the curve. It's like, imagine that you were making some kind of something with Play-Doh or clay or dough, something bread, right? And you have this very odd shape. Could you not mush it around in such a way that it actually forms some other shape? Yes, you can. You can do that, and you can do that with the area under the curve too. All you're doing is you're shifting pieces of the area. It's like shifting sand. So this piece that's a little bit above should be the same as the piece that's a little bit below and missing area of. Okay? The calculation for it's very easy. It's just this one extra little piece at the front where you multiply by 1 over b minus a. So let's actually take a look. And again, you can actually give the answer. When you do the answer, you can check your calculator. And visually, you can confirm that your answer makes sense. So we will do that. All right, so let's find the average value of the function on the interval that's given, which is from 4 to 9, of the square root of x. So according to that formula on the previous slide, we should be taking the integral from 4 to 9 of the square root of x, but I don't really think that it's helpful to have it written as square root, so we'll write it as x to the 1/2. Okay, you guys good? All right, so we're going to actually do the calculus for that. We'll do the picture for it in a second, but let's do the calculus first. What's the antiderivative of x to the 1/2? Okay, so we're going to have x to the 3/2. We would divide by that 3/2, or that's the same as multiplying by 2/3. So either divide by 3/2 or multiply by 2/3. If you multiply by 2/3, you keep the fraction inside of a fraction thing from happening. We're wanting to evaluate this at 9 and at 4. And you can use your calculator to do that. You could also go ahead and change this notation to help you out to recognize that this is the square root of x cubed from 9 to 4, which might help you in calculating it if you're doing it by hand, or if it weren't, in fact, a nice whole number that's going to come out of this thing. So we're going to have the square root of 9 cubed minus 2/3, and then the square root of 4 cubed. All right, so what's the square root of 9? 3, thank you. And 3 cubed is 27. And then we have 2/3 times 27, which would give me what? It would be 18. And again, you're welcome to grab your calculator for it. It doesn't bother me at all. Square root of 4 is 2. 2 cubed is 8. So then we have 2/3 times 8, which would be 16/3. And if we subtract this, we're going to end up getting what? 38 over 3. Now, I left it off, and so let's go back and put it in now. This would be calculating this, but at the very front, we were supposed to have 1 over 9 minus 4, right? 1 over b minus a. So what is 1 over 9 minus 4? It's 1/5. So I'm going to go back in, and I'm going to put a 1/5 everywhere. If we'd been doing it all the way along, if I were paying attention better, we would have been able to do that in advance. But we can do it at the end just fine. Doesn't hurt a single thing. So then what is the 38 over 3 times 1/5? What is it? 38 over 15. Okay, so that's the average value. 38 over 3 is the area under the curve. The average value is 38 over 15. So how can you use your calculator to confirm that that's at least a reasonable answer? Well, I'm going to graph it, right? What are you going to graph? Which function? I mean, we've manipulated things in here. What am I going to graph? The original function, right? Square root of x. Okay? So hit y equals, put in square root of x. Our window right now, because we were using it just a minute ago, went from -10 to 10. I'm sorry, -5 to 5. That's what we left it at. Let's just put it back in that standard window. So hit zoom 6. And you'll have your standard graph window. So right now, your screen looks something like this. Okay, does it look like that, roughly? Okay. Let's let our calculator calculate that area like we did just a minute ago to go from 4 to 9. Okay, so how do we do that? Well, we hit second, trace, option 7, lower limit 4, upper limit 9. So your calculator has now shaded in this area right here. Now, if you had one of the newfangled calculators where the screen's in color, what I'm about to do would make a little bit more sense. I need that to go away, though. I need that shading probably to go away because otherwise you're not going to see. Well, actually, let me show you the line so you can see why I need it. Go hit y equals. And in y2, I want you to put the average value that we just got, so 38 over 15. So right now you've got x squared, or square root of x in y1, you've got 38 over 15 in y2, and then just hit graph. It's hard to see, isn't it? I mean, you can kind of see how that line's cutting through, but it's hard to see that it's really balancing the values. So let's actually attempt to do this slightly different way. I want you to hit window. Let's do this. Let's just make our window go from 4 to 9. So x minimum 4, x maximum 9, and then hit graph. We might even want to change our y minimum to 0. That might be helpful too. Yeah, that's a little bit more helpful. So make your y minimum 0. You can even make your y maximum smaller if you want. So let's do this. For visual sake right now, our x minimum should say 4. Our x maximum will say 9. Our y minimum can be 0. That's the x-axis. And if you really want to see it really well, let's make your y maximum. What do I have mine at right now? Let's make our y maximum 5. I think that might be easier. And then hit graph. Oh yeah, that's better. Okay, so right now the curve that I'm getting almost doesn't even look like a curve. Okay, that's really thick. My screen this is my screen right now, and it looks something like this and this. Does yours look something like that?
I don't know how to do the average.
How to do what?
The average.
You just plug in the number in Y2.
But in Y2?
Yeah. Okay, so my picture on my screen is not super convincing, but hopefully as you're looking at your one on your calculator screen, you do see the convincing part of it, right? It looks like there's a balancing between what's above the curve here and what's below it over here. So that's convincing. If you didn't see them intersect, that would be a problem. You know you did something wrong, right? If it didn't look balanced at all, like it was way top heavy or bottom heavy somewhere, you'd know you did something wrong, and that would be a clue to go back to actually make sure you had had the values in the right place, or didn't miss a negative sign or something like that. Any question on this one? All right.